Welcome to my YouTube channel. In this video we are going to learn how to use the series solution method to solve the differential equation part 3. The differential equation we are going to be looking at is the Helmholtz differential equation, and it's giving us this. So we have d squared y dy squared plus k squared y equal to 0, where the k here is a constant. Our k here is a constant. Now, as usual, we assume that the solution of this particular equation has this form, which is presented below. So where our a subscript n and our x raised by r plus n are parameters that are related to the y. So our aim is to determine the value of a subscript n, and also the value of r. Once we know those values, then we are done. So the expansion of this equation, as usual, is giving us this. So this is the first term, which is the 0th, a0 x r plus 0, a1 x r plus 1, a2 x r raised by r plus 2, and so on and so forth. So once we know this value, we know this value, we know this value, we know this value, and the r, then we can fix them here, and that will be the solution. So the next thing is for us to differentiate this particular term with respect to y, with respect to x twice to get this term. And to do so, we have to differentiate once first, which is this term. Our r plus n comes back when you differentiate, and you now have r plus n minus 1. So let's differentiate the second time, and in so doing, these parts will come back having r plus n minus 2. So and that gives us this term. So now what we need to do is to substitute this equation into this expression here, into this equation, and let's see what it gives us. Okay, so this is the left hand part of the expression, and this is the right hand part of the expression, which is equal to 0. So from this expression we can send our k squared in, and that becomes k squared this and this. So at this point we need to get our initial equation, and that initial equation we need to concentrate on this part, and from these parts we set our n equal to 0. So wherever we see n, we'll set it to 0. That will give us the initial equation for a0, and in so doing we have something of this form, right? We'll bring out this one out and set in our n equal to 0. So when you put your 0 0 0 0, this one will now reduce to these parts. Now we can see that this part here, as usual, if you check the previous videos on series solution, you realize that this x raised by r plus minus 2 is not found in that usual expansion of y. So because this one is not found, all other terms that are found are x r plus 1, x r plus 2, x r plus 3, and so on and so forth. And for the fact that this one is not found in that series, then the coefficients of this expression, that is everything here, must be equal to 0, and that leads to a0 r minus 1 equal to 0. Now, as usual, because our a0 is an important parameter that cannot be equal to 0, based on the fact that all other parameters like the a1, a2 can be dependent on it, so therefore this expression should be the one that will be equal to 0. So and that leads to r equal to 0 or r equal to what? 1. So we have two parts of the solution now, when r equal to 0 and when r equal to 1. Okay, so we go back to this same expression and find the initial equation for when a equal to 1. And why is it so? Because we have n minus 2. For the previous videos where we had n minus 1, once we get our r, then we'll go ahead and get the recurrent relation. But now this one is n minus 2. We need to get the initial equation for a0 and for a1. So let's see how the a1 will look like. So we'll still go back to this expression, and we'll simplify by setting n equal to 1, n equal to 1, and n equal to 1 for these parts. Also, if we simplify these as parts, it gives us a1 r plus 1 r, these two will cancel out to give us r, then x r minus 1. Also, this part is not found in the series of y, the expansion of y, so therefore everything here will be equal to 0. So that leads to this part equal to 0. But mind you, we have already found that our r equal to 0. So if r is 0, it goes off. If r here is 0, it goes off. So you are left with a times 1 equal to 0. So that means a1, a subscript 1 must be equal to 0. Or we can say, since r equal to also 1, if I put 1 here and I put 1 here, this one will be 2 times 1, which is 2. So a1 times 2 equal to 0. 2 can never be equal to 0. So a1 therefore becomes 0, which leads to this one. So if that's the case, we have established the fact that a0 can never be 0, but a1 is equal to 0. So let's go ahead, let's go back to this expression and get the recurrent relation. Okay, so back to this. Now to get the recurrent relation, we just set an. We want to make this expression exactly like this, and to make it exactly like this, we need to do something to these parts to make this one look exactly like this. And what do? Wherever we see n, we put n plus 2. So if I see n, I put n plus 2. So that gives us this part here. So this is a, n plus 2. This is n, n plus 2. This is n, n plus 2 minus 1 will give me plus 1. Then n plus 2, 2 cancel. So you see exactly this one matches this one. So we can simplify this one by factorizing our x r plus n out and take one summation. And that gives us one summation with all this one having k squared a n x r. So with this, it shows that everything here should be equal to 0, because if this one and this summation takes care of this, then we have this one left. So we have our an plus 2, this one, this one, this one. So as usual, we need to make a subscript n plus 2 the subject formula, and in doing so, we send this one to this side, then divide both sides. So this is what we have. So we have an plus 2, we have this one equal to this, then followed by an plus 2 equal to, sending this one down, we have this one. Now remember, our r, we have found out that it is equal to 0 or 1. So we have two possibilities for this particular expression, which is a recurrent relation. So let's see the two possibilities. So the first possibility is when r equal to 0. So if I set my r equal to 0, it becomes n plus 2. If I set my r equal to 0, we have n plus 1. Also, if I set my r equal to 1, which is this, and this one, which is this, then this particular one will be for r equal to 0. This one will be for r equal to what? 1. So these two will become n plus 3, n plus 2. So now let's concentrate on this part and solve for when r equal to 0 and get the series. Then we'll later come back to this one and solve for this series. So okay, so this one is a reduced form of r equal to 0, and this one is a reduced form of r equal to 1. So for r equal to 0, if you put your a0 here, what would this part be? a2. So a0 minus k squared, then this one is 0, 0. So here will become 2 dot 1. Since we are setting, wherever we see n, we'll put 0 in this part. So this is what we have. Then we can also use the same method to get for a4. But remember, if you put 1 here, here will be 3. But since we found out that a1 is 0, that means a3 must be 0. If a3 is 0, here a5 here must be 0. So all odd numbers of a subscript n is equal to 0. So we'll concentrate only on the even numbers. So that's what we are going to do for a4. So for a4, when you put 2 here, here will be 4, because 2 plus 2 is 4, 2 plus 2 is 4, 2 plus 1 is 3, then a2. Well, we already know our a2 to be this expression, so if you substitute, you get a0k raised by 4 all over 4 factorial. So you can also do for a6, and that gives us this one, a6. You can confirm that. Okay, so remember, this is the expansion of our y. We already found out that r equal to 0, r equal to 0. So wherever I see a0, we substitute the value. Wherever I see a1, we'll put 0. a2 will put the value, a3 will put 0. So that leads to y1, which is the first solution, equal to a0 x 0 plus 0, which is this, a2, which is giving us this, all over 2 factorial, a4 is this part minus the other parts. So we can factorize a0 out, because this one will give me 1, and that gives me a0, factorize them out, 1 minus k squared x squared 2 factorial, k4 x4 4 factorial. So that's the solution for the first one. And if you look at this one, it looks like one of the common series that we know of, and that gives us the cos kx. So y1 is equal to a0 cos kx. So let's go ahead and solve for the second one. For the second one, this is where we start from. So I will put our knots and put 2 there. So we'll substitute the value of n equal to 0 to get for a2. So a2 is giving us this. We can solve for a4, which is giving us this. You can confirm these expressions. Then we'll substitute into this expression. So at the end of the day, we'll make the substitution for a0, a2, and a4. I think this one was an omission. It's supposed to be a1, a2, a4. Sorry, a0, a2, a4, then a6. Yeah. So sorry for the mistake. So we have our y2 equal to a0 x1 minus, this is the a2, this is the a4, and this is the a6, right? So by the time we factorize, because x1 is common throughout, then we have an expression of this form. So at the end of the day, we have y2 equal to this expression. So but this expression is not a common series expansion. It's not common. So what we can do is to multiply the top and the bottom by k, and we have this expression. So we can send our k in, so that it becomes xk. This part will become k cube with x cube. This part will become k raised to power 5 with x5, and so on and so forth. So that leads to this expression. So leaving our a0 all over k. So from this expression, we have that this a0 all over k, which is a constant, we can call it b0, and we have this b0 kx. So with this expression now, this one looks like a very popular series, and that series is the sine series, which is giving us y2 equal to b0 sine kx. So from this expression, we can now say we need to combine y1 and y2, which will give us the final solution. So y is equal to y1 plus y2. Remember, y1 is a cos kx and y2 is b sin kx, and this solves the final, this is the final solution for the solution series. Thanks for watching. Please like, share, and subscribe to my YouTube channel. Thank you.